Lecture we will be learning the design of counterfort retaining wall. In the first lecture I have given you the classification of different types of retaining walls, out of which one was this counterfort retaining wall. So what is this counterfort retaining wall? The counterfort retaining wall consists of a stem, a toe slab and a heel slab, and apart from these, a very distinctive feature is these triangular elements, slab-like elements provided along the height of the stem and supported at stem as well as the heel slab like this, and are provided at a particular spacing along the length of retaining wall on the backfill side. So a completely constructed retaining wall, counterfort retaining wall, in a completely constructed retaining wall we will not be able to visualize these counterforts as these are on the backfill side. So the presence of these counterforts affect the overall structural behavior of other components of the cantilever retaining of the counterfort retaining wall also. Therefore, its design and behavior is entirely different from that of cantilever retaining wall. Now I have collected some pictures from the internet of different cantilever counterfort retaining walls being constructed at site. Here you can see the provision of counterforts along the height of stem at a particular spacing, and also the reinforcement here and here in the counterforts, like this mesh type reinforcement here and this inclined reinforcement here. So we will be learning in the coming slides how this reinforcement is provided and designed. Now before proceeding further, we must know the application of counterfort retaining wall. Like I have told you before, the counterfort retaining walls are provided for retaining backfill of height greater than 6 meter, and cantilever retaining wall are provided for retaining backfill up to a height of 6 meter. So the question here is, why cannot we provide cantilever retaining wall for more greater heights, that is for height greater than 6 meter? So the reason is that for very high backfills having height greater than 6 meter, if we provide cantilever retaining wall, the wall will come out to be very uneconomic and unsuitable. So the reason behind this is very simple and clear. For this you will have to go back to the cantilever retaining wall behavior. So I am taking an example of the stem. The stem is fixed here. So as you know, the moment acting at this particular fixed end of the stem is m base is Ka gamma h cube upon 6. As you can see here, the moment is directly proportional to the cube of the h, that is the height of backfill. So more is the height, more is the moment at the base. Also, you know another relation, that if we have to find the thickness of stem at this particular point, that will be found out by d is equal to under root m upon rb. So if more is the height, more is the moment, and more is the d. Therefore we can conclude that due to large height of backfill, more moments will result in more thickness, and this will increase the overall weight as well as cost of the retaining wall, as we know that thicker sections lead to more material consumption and more bulkier sections which are not desirable. Also, for other parts of retaining wall, for example the thickness of your base slab depends on the height of the backfill. Look at this point here. I have taken example of the base slab. Thickness of base slab is assumed to be 1/10 to 1/15 of h. So h is the height. So more is the height, more will be the thickness of base slab. So we can easily conclude that more height results in thicker sections and bulkier sections, which result in uneconomic wall. So therefore, in order to provide high backfill retaining walls, we need to reduce this moment. We cannot change the height of the retaining wall, so we need to reduce this moment by some way, so that the total the depth of the sections or thickness of the sections come out to be desirable and not much large. Therefore, counterforts are the solution for that. The provision of counterforts in retaining wall reduces the toting on the wall due to the large height. Therefore, counterfort retaining walls are provided and are economic and most suitable for heights greater than 6 meters because they reduce the bending moments and hence lead to economic sections. So this is the very important point, that why counterfort retaining walls are required. So how these counterforts reduce the moments we will be studying in the coming slides. Now we must know what are the different types of loads acting on the retaining wall on different components. So I have explained it here one by one. So first is the stem. As you know from the previous case of cantilever retaining wall, the stem is acted upon by the lateral active earth force as shown here. But the behavior of cantilever retaining wall is quite different from the counterfort retaining wall. How? For this I will first draw here a cantilever retaining wall so that the picture is more clear to you. In the cantilever retaining wall, if we look at the stem was fixed at this particular portion and free here. So whenever lateral force acted on this stem, this stem behaved like a cantilever. But now when we provide now I am changing it to a counterfort. When we are providing a triangular element here or here on the stem, so what will happen if this is a counterfort? This side is no longer free to move. Therefore this hole cannot behave like a cantilever, because in cantilever one end is fixed and one end is free. Therefore the behavior of stem cannot be like the cantilever as in the previous case. So how will the slab behave? We will be studying in the coming slides, but for now you must know that if the counterfort is provided here, then this edge of your stem is supported by counterfort. Therefore this edge is also fixed. This edge of stem is also supported by the counterfort, and this edge is supported by the heel slab. Therefore the stem is supported on the three sides as shown here with the help of small lines. So we can easily say that the stem behaves like a vertical continuous slab fixed on three edges and subjected to uniformly varying load due to the earth pressure. And in the cantilever retaining wall, the stem behaved like a cantilever slab which was fixed at only one edge, that is the heel slab. So I hope this is clear to you. Now next is heel slab. The heel slab is acted upon by two forces. One is the downward weight of the backfill. As this portion is filled with backfill, therefore its weight will act on the heel slab. Apart from that, upward soil pressure will also act on the heel slab. This is the minimum. Now when we have to calculate the resultant force, as this is downward, this is upward, when we calculate the resultant force, we know that the downward weight force will be always dominating the upward force because its value will be more due to the large height. Therefore if this downward force is more than the upward force, the net force or resultant force will also come out to be downward. Hence we can easily say that the load acting on the heel slab is the net resultant downward load acting due to the downward weight of backfill and upward soil pressure. And if we calculate this load, its distribution will be like this. It will be a trapezoidal load with maximum value at the edge and minimum at the junction with the stem. This value is coming out to be maximum and here it is minimum. It is very clear. If this value is larger and this is smaller, then if we, for example, I will give you an example. If the downward weight is 40 and the P minimum is 10, therefore the value at this edge will be 40 minus 10, that is 30. Now as we move towards the stem in this direction. Here this value will be also 40 because this is a uniformly UDL, uniformly distributed load, and this value will be slightly higher than P minimum because the soil pressure is increasing towards your stem or towards your toe slab. So if this value is 15, this value is 15 and this value is 40, then this value will come out to be 25 and so on. Hence this trapezoidal load keeps on decreasing towards the stem, and which is inverse to that of the soil pressure acting upwards. So the net force will be like this, but we will be more concerned with this maximum force 30 or whichever value this is acting on the edge of your heel slab. Kindly note here that this trapezoidal load is acting same at all the sections of your heel slab. Like this load will be traveling, acting here also, here also, here also, here also, in this direction. So the maximum values we will be getting at this particular edge, that is the outermost edge of your heel slab. So I hope it is clear to you what is the action of your heel slab. And one other thing, as in the case of the stem, the heel slab is also supported on 3 edges. This is the edge of the heel slab supported on the stem. This edge of the heel slab, which was earlier not supported, but now it is supported by the counterfort here, and this edge is also supported by counterfort. Therefore heel slab also behaves like a slab fixed on 3 edges and subjected to uniformly varying downward load, which is shown here. Now next is toe slab. As there is no counterfort provided on the front side, that is on the toe slab, therefore this edge will be free. If there was a counterfort provided here, like in the case of buttress retaining wall, then the same behavior as we studied in the previous slide will be shown by toe slab also. But as there is no counterfort here, this will be free end and this will be always fixed due to the presence of stem here. Therefore the behavior of toe slab is same, that is like a cantilever fixed on the stem junction and free at the other end. So its behavior will be the same as that in the cantilever retaining wall, and the load acting will be the upward soil pressure acting on the heel slab and toe slab, and the downward weight of soil, this can be neglected because this is very less height, so this load can be neglected as we did in the previous case. Now the next component of the retaining wall is counterfort. The counterfort is acted upon by 2 types of forces. First is the lateral active earth force acting in this direction, and the second is the weight of the backfill. The counterfort will be embedded in the backfill present here, so its weight will also be transferred to the counterfort. So these are all types of loads acting on the different components of counterfort retaining wall. Now we will be studying in detail the structural behavior and design of each part of counterfort retaining wall. So as it must be clear to you by now, the structural behavior of counterfort retaining wall cannot be same as that of a cantilever retaining wall, because in counterfort retaining wall, the stem and the heel slab do not behave like cantilevers, but they behave like slabs supported on 3 edges, while the toe slab behaves like a cantilever. So we have to study these behavior individually, and also we have to study the behavior of the counterfort, additional item provided in the counterfort retaining wall. So first we will look at the behavior of stem. So the stem behaves like a slab supported on the 3 edges. So for under the basic understand, it is acted upon by lateral active earth pressure like this, with maximum value at the bottom. So if in this triangular or uniformly varying load, the maximum value will be at the edge of your stem where it is meeting with the heel slab like this. So we are concerned with this load only majorly because this is the maximum load acting on the stem. This load will keep on decreasing as we move upwards. So this is the stem acted upon by this load. This is lateral direction. Okay. Now for this we must recall the concept of the slab which we studied in the previous course, Design of Concrete Structures 1. So you must remember now that if we have a slab, either one-way slab or two-way slab, if a load is acting in this direction, then what will happen to the slab? It will deflect like this. As this is not a cantilever slab, it will deflect like this. If it had been cantilever, the deflection would have been reversed. So if this is type of deflection, so where is the positive moment coming, or where is the sagging coming? That is in the bottom face. So therefore positive bending moment or tension is acting on the bottom face of your slab, and compression is on the upper face. Okay, so is it clear to you? Now let us recall another case. If the edges of these this slab are fixed, so what will happen? For this you will have to recall the design of continuous slab or continuous beam. So if, let me draw a L section of your slab. If we have a slab in which this is one support, this is another support, and this is a continuous slab or a continuous beam, whatever the case may be, and load is acting in the downward direction. So what is the behavior of such type of slab? Due to this vertical downward load, the middle span of this, the span between the supports, the middle span of this span will deflect like in the downward direction, and due to the presence of this fixed support or support, the outer face or the top face of the slab will show tension on the outer face. So I will draw this like again. So the middle portion deflects like this, as sagging is on the midspan, and due to the presence of the supports here, there will be a little such type of deflection or movements here. So what does this mean? That the positive bending moment are acting on the bottom face of your slab in the mid region due to the sagging here. This, the bottom portion of the midspan of your continuous slab undergoes sagging or positive bending moment or tension, and due to the presence of these supports here, the outer portion or the top portion of your slab undergoes sagging, positive here, and therefore tension here. So the outer face or the top face will be under tension. So what we do about the reinforcement in such cases? You have studied all this in previous course. If such case is with us, we provide reinforcement in the midspan on the bottom face and reinforcement in the top face near the supports. So we have two type of main reinforcements. One is in the midspan and one is near the supports on the top face. So this concept is applied here in the stem also. So how is this stem similar to this continuous slab? Now picture this portion of stem as a slab. Now this portion of stem as a slab, or this portion as any portion of stem you can take. Now in this stem, what is happening? What is happening? Due to the load acting in this particular side, this is the load acting on this particular stem, and this edge is fixed and this edge is also fixed. Therefore these are the continuous supports. Both these supports are continuous. So what will happen? Due to the presence of these continuous support, negative bending moment will be near the supports, that is near the, what are the supports here? Near the counterforts. And in the middle portion there is no support, therefore the tension will be on the outer face. So I repeat, if this is a slab here and this is the load acting on this slab, so tension will be on the outer face in the midspan region and tension will be on the inner face in the support region. Look at this diagram here. This is the stem portion. The tension or sagging in the midspan region is here, and the sagging is like this in the top, in the inner face like this. So this will result in tension here, and this will result in tension here and tension here. So what will happen? Due to this, we provide reinforcement. Due to this positive bending moment, we provide reinforcement here, and due to this tension here or negative bending moment at support, we provide tension reinforcement here and here on the inner face. So like that, in a continuous slab we provide two types of reinforcement, one on the outer face, which is the main reinforcement due to positive bending moment at midspan, and second is on the inner face, main reinforcement on the inner face due to the negative bending moment near the counterforts. So this reinforcement will be provided at a specific interval. Here the red is showing the inner face reinforcement, that is the negative bending moment reinforcement, which is equally provided along the stem height, and the blue is showing, and this blue is showing this positive bending moment reinforcement, which is provided distributed equally along the height of your stem. So I hope the reinforcement part is clear to you, how this is provided. I have enlarged here for better understanding of yours. So how do we calculate these reinforcement? We have to calculate the positive bending moment and the negative bending moment at the midspan and the supports respectively. So positive bending moment at midspan of the stem on the outer face is WL square by 16, and negative bending moment is WL square by 12 near the counterforts on the inner face. And the W here is the maximum pressure, soil pressure acting on the stem, which is Ka into gamma H. So I hope this concept is clear to you. I will be explaining it in detail when we do the design problem. Therefore, to summarize, the stem of a counterfort retaining wall behaves like a continuous slab supported on three edges, in which the outer face is subjected to the tension due to positive bending moment near the midspan of the slab, and the inner face is subjected to negative bending moment and hence tension due to the presence of the supports, that is these counterforts. Therefore the reinforcements are provided in the horizontal direction along the length of your across the length of your height of your stem in specific spacing in the outer face as well as on the inner face. In outer face we provide reinforcement near the midspan, and in the inner face we provided it near the supports or counterforts. So I hope this concept is clear to you now. Now we will look at the behavior and design of heel slab. So heel slab also behaves in same way as that of a stem. Its edges are on the three edges, are fixed at three edges or supported at three edges like this, and the load acting is maximum at this free edge of your heel slab. This free edge is acted upon by the net downward force, which is acted due to the downward weight of soil and the upward soil pressure. This is the resultant load. So this will be the maximum force. I call it P. Now what will happen due to this P, as we learnt in the previous slides, due to, if we consider it as a continuous slab, the tension will, due to this particular load, the tension will be on the outer face in the midspan. Now you have to ignore all these loads, as this is a trapezoidal load. Ignore all other loads, just take the maximum load. So if this is your slab and these are the, if this is your slab, heel slab, this is the stem here, and this is first counterfort, second counterfort, and these are the loads, net downward load. Then due to this downward load, how will the slab deflect? In this way. So tension will be on the bottom face, but due to the presence of counterforts here, there may be some negative moments here like this also. Therefore what will happen? Tension will be on the top face also at the supports. This concept is exactly similar as that of a continuous slab or a continuous beam. So in this particular section of your heel slab, the tension will be on the outer face near the midspan or the bottom face, and tension will be on the top face near the counterfort. So the reinforcements are provided accordingly. Therefore negative bending moment at counterfort support causes the tension on the top face near the counterforts, and the downward forces also lead to positive bending moment near the midspan. So that is the positive bending moment reinforcement. So main reinforcement is provided along the heel slab in the bottom face and at top face near the counterforts due to the negative bending moment. So now again look at this diagram. This will be tension near the midspan, tension will be on the outer face, and near the counterfort support, the tension will be on the inner face. Therefore reinforcements are provided due to this positive bending moment. Reinforcements are provided like this in the middle portion on the bottom face, and due to this negative bending moment, the reinforcement is provided like this and like this on the top face. So I hope this concept is clear to you. The positive and bending moment will be same, PL square by 16 and PL square by 12. Here P is the maximum value of this load acting on the downward load acting on the heel slab edge. So this is the positive reinforcement at bottom and the negative reinforcement at top. I hope this is also clear to you. Now for the toe slab, the design and behavior will be exactly like that of a cantilever slab, cantilever toe slab. I will not explain you the design of cantilever toe slab in the cantilever retaining wall question. So this will be exactly similar. The toe slab will be acted upon by the upward soil pressure, and therefore due to this the tension will become on the bottom face like this. So the main reinforcement is provided here, and the other distribution steel are provided. So the design of toe slab is same. Now comes the design of counterforts. So counterforts are triangular beam elements. It behaves, we assume it to be a T-beam of varying cross section. This is the flange of your T-beam and this is the web of your T-beam, and it has varying depths at different cross sections. Like this is the depth of the T-beam here, this is the depth here, this is the depth here. So this behaves like a T-beam of varying cross sections, supported at two edges. AB is supported on stem and edge BC is supported on your heel slab. The outer face AC, this particular portion will be in tension. Outer portion of this will be in tension due to the downward weight of soil as well as the P force acting on the counterfort. Now when we design this counterfort, then the depth we will take, as the depth is varying along different cross sections, the depth we will use for calculation will be this, the maximum depth, which is if we look at this triangle ABC, the BB dash will be the depth. That is, if we draw perpendicular from right angle B point towards the AC, then BB dash will be the depth of your counterfort. The maximum moment at base of the counterfort will be Ka gamma h cube upon 6, as in the case of stem, into L. We are taking L here because we know the distance, this much portion of your retaining wall. This is also one counterfort, this is the second counterfort. The spacing is known to us. Previously we were taking L to be 1 meter because we are already calculating moments, kilonewton meter per meter length of the wall. Now this length is known, that is the spacing of counterforts. So maximum moment at base is this. So before we design the counterforts, we have to assume the spacing, which is taken as 3 to 3.5 meter, and the width of this counterfort. This width has also to be assumed, which is taken as 0.05 h, or in some cases it is also taken as same as that of thickness of the base slab. Now we will look at the action of these two forces, lateral active earth force and weight of backfill acting on this particular counterfort. So what is happening, if this is a counterfort and this is P acting on the counterfort, this P will try to push this counterfort backward, and hence it will try to separate the counterfort from the, this is the stem here, it is supported on stem, so this P will try to separate it from the stem. So apart from the other reinforcement provided due to this maximum bending moment, horizontal ties are provided in the counterfort so that this P force cannot separate the counterfort from the stem. Similarly, the downward weight of backfill will try to separate the counterfort from the heel slab. Therefore, we provide vertical ties. So these two reinforcements will be like this. If we provide them together, they will be provided in the form of mesh. So if you remember in the I think first or second slide of this presentation, where I showed you the different pictures of counterfort retaining wall, such mesh was provided in the counterfort. So this is that mesh consisting of the vertical and horizontal ties to resist the P force and the W force. So we'll be learning with the counterfort design later when we do the design problem in detail. Understanding, let us do a design problem of counterfort retaining wall. Now the question is to design a counterfort retaining wall to retain 4 meter high backfill above the ground surface, and the soil properties of the soil are given to us. So the first step is the calculation of the minimum depth of the retaining wall, which we have to provide below the ground surface. Also we have to extend the retaining wall further downwards in the ground surface, below the ground surface. So the H minimum formula is this, as I have explained to you in the previous design problem also. So this comes out to be 1.5 meter. So the overall height will be 4 meter plus 1.5 meter, hence 5.5 meter. So total height of retaining wall is 5.5 meter, out of which 4 meter is above ground. Now preliminary dimensioning is done almost same as that of cantilever retaining wall. So the width of base slab is taken to be 0.4 h to 0.6 h, so we get it 2.2 to 3.3 meter. So we assume any value in between 3 meter. Width of toe slab is 0.3 to 0.4 h, sorry 0.3 h, sorry 0.3 b, therefore 0.3 into 3.9 meter. You can also take it to be 0.4 b. Thickness of base slab is assumed like this. Now spacing of counterforts is 3 to 3.5 meter. I have taken it here to be 3 meter. Width of counterfort, that is this portion. If this is a counterfort, this width is assumed to be 0.05 h, so 0.3 meter, and thickness of stem is taken as to be same as thickness or width of counterfort, 0.3 meter. So this is for practical condition. The thickness of counterfort is almost kept at the same as the thickness of your stem. So we have done it, taken is 0.3 meter. In the cantilever retaining wall, we calculated the thickness of stem by using the cantilever moment. Now we don't have to do it here, you can just take it same as that of the width of counterfort. So we get this diagram of your counterfort retaining wall. 0.3 meter is the thickness of stem, 0.9 meter width of toe slab, 3 meter width of overall base slab, 0.5 meter is the thickness of your base slab. So what will be the height of your stem? Total height is 5.5 meter. If we deduct the thickness of base slab, we get 5.5 minus 0.5, that is 5 meter as the height of your stem. So when we have assumed all these values, we will apply the stability checks. For that we will first calculate all the forces and all the moments. So I have already explained this part to you. So what we do, we calculate all the weights and all the lateral earth forces, and we calculate the lever arm, and we calculate restoring moment and overturning moment, and combine all these together. And then we apply the stability checks, that is check for overturning, check for sliding, check for safety of under soil. So here you can see overturning check, factor of safety for overturning is 2.4, which is okay. Factor of safety for sliding is 1.49, which is also okay. And P maximum is 123.06, which is less than the Q naught, which is the safe bearing capacity of soil. It is also okay. And the P minimum is positive, therefore okay. Hence all the assumptions in this retaining wall are fine, and we can proceed further with the design of counterfort retaining wall. Now first of all, we design the step. So in this case, as this is not a cantilever, so we don't need to find any cantilever moments. We just find the value W. What is W? This is K into gamma H. This is the lateral earth force acting at the base of your stem. So this is K into gamma H. Ka is 1 by 3 into 15 is gamma, and H is 5. H is the height of your stem. We get it to be 25 Newton per meter square. So if we take unit length of your stem, it will come out to be 25 kilonewton per meter. So now we calculate the maximum positive bending moment and maximum negative moment due to these W. So maximum positive bending moment is this. We multiply this moment with 1.5 to get the design moment, which is coming out to be 21. Similarly, negative moment is WL square by 12. Here L is the length of the spacing between two counterforts, which is assumed to be 3 meters. So we get design negative and design positive bending moment. So we will apply check for the depth of stem. Here in the previous step, we have taken the thickness of stem to be 0.3 meters. So we will check whether this thickness will be sufficient to support the moments or not. So what we do, we take the maximum of these two values, because the maximum value will lead to maximum thickness required. So the D required will come out to be 101 mm, and we have the total thickness we have provided as 0.3 meter, 300 mm. If we assume 50 mm cover, effective cover, then 250 mm is the D provided. So 101 is less than D provided, or the 250 mm is greater than the minimum required value, hence our assumption is okay. Now calculation of reinforcement. We calculate reinforcement due to the positive as well as negative bending moment. First I take the higher value, that is 28. So always take the higher value first. Reason I will explain to you now. First calculate mu negative, which is reinforcement due to mu negative. It is coming out to be AST is equal to 320 mm square. Now we will compare it with minimum AST required, which is 0.12% of cross section of stem. It is coming out to be 360. So AST required is 320 and AST minimum is 360. So we have to provide at least 360 mm square this is the minimum prescribed value, hence we will provide the minimum reinforcement. So we assume the diameter of bars and calculate the spacing. So we get 10 mm dia bars at 200 mm center to center, and this is for the negative moment. So this is along height of stem near the counterfort due to the negative moment on the inner face. Now, do we need to calculate Mu positive reinforcement due to Mu positive also? So as Mu positive is 22 with 21, which is lesser than 28, therefore AST positive will also come out to be less than 320, and therefore it will be also less than AST minimum, that is 360. So in the positive moment direction also we provide the minimum AST, hence we can calculate. We do not need to calculate it, although you can calculate. I have calculated it here for your understanding. This value is coming out to be around 300 mm square, which is less than AST minimum. Therefore here also we will provide the 10 mm dia bar at 200 mm center to center, as in this case. Okay, now what is this distribution steel? So now we have provided the reinforcement, horizontal reinforcement in stem like this. So as you know, we cannot provide the reinforcement like this only. We have to provide a certain amount of reinforcement in the opposite direction also. So distribution reinforcement equal to the minimum reinforcement is provided in the perpendicular direction, that is the vertical direction, on the inner face also and on the outer face also. So note here, when we compare it with the cantilever stem, in cantilever stem of cantilever retaining wall, the main reinforcement was the vertical and distribution steel was horizontal. Now here the main reinforcement is the horizontal reinforcement and the vertical bars are the distribution reinforcement. So for clarity, I have drawn the sections of your stem on outer face and inner face separately. On outer face we have tension due to the positive bending moment acting at the midspan, so we get the main reinforcement as this, and the distribution steel is vertical. In the inner face we have the tension on the inner face near the counterfort, so we provide the main reinforcement horizontal like this and the vertical distribution reinforcement like this. Now look here, if you look here closely, in the bottom portion of stem I have kept the spacing as 200 and in the upper portion as 300. It is because as we move upward, the value of W, which is the base pressure acting on the stem, keeps on reducing. Therefore reinforcement is not required much in the above portion, so we can reduce it in the upper portion. You may or may not do, it's up to you. Similarly in the inner face region also we may reduce the reinforcement or increase the spacing towards the top of your stem, because the pressure will also increase. So this is the reinforcement detailing of a stem on the outer face and on the inner face. So if you see the plan of this stem, it will look like this. On the outer face we have midspan reinforcement, and on the inner face we have the support reinforcement near the supports or counterforts. This will be the plan of your stem. Now we do the design of heel slab. For that, first we will have to calculate these forces. So what is the downward weight acting on this heel slab? This is the downward weight of backfill plus the self weight of slab. So downward weight will be the height into density of soil, so 5 into 15, and self weight of slab will be 0.5 into 25. I am taking both these values in kilonewton per meter square because the pressures are, the upward soil pressure is also in kilonewton per meter square. So for we need to find the resultant value, therefore we have the units have to be kept same. So the downward weight of backfill is this, self weight is this. We add both these to get the total downward weight as 87 kilonewton per meter square. And P minimum and P maximum we have calculated during the stability check. So we are concerned with this the force at the edge of your heel slab only, this force. because this will be the maximum. Therefore maximum downward pressure acting on heel slab will be the total weight, downward weight, minus the P minimum, which is coming out to be 70.56. Therefore in the net downward load, net resultant downward load, this value will be 70.56, and this will act like this in the heel slab edge. So we are concerned with this force also only. So due to this load, the tension will be on the outer face in the midspan, and due to these supports present here, tension will be also on the upper side due to the negative bending moment. Therefore reinforcement will be also provided here. So we calculate negative and positive bending moments. Similarly, and in the previous question, we do the check for thickness required. The thickness of the base slab was kept as 0.5 meter, and we take the higher of these moments and check D required. It is coming out to be 169 mm, which is obviously very larger, quite less than 440 mm. 440 mm is the 500 minus 60. 60 is taken as to be the effective cover in the base slab. So D required is less than D provided, hence the thickness provided of the base slab is okay. Now we calculate the reinforcement as done in the previous step. The mu positive is 60 and mu negative is 79, so I will calculate mu 79 first, which is negative reinforcement. So negative reinforcement is coming out to be 512 mm square, and the minimum AST is coming out to be 600 mm square. So as in case of stem also, the minimum AST was greater than the AST required, therefore we provide area of reinforcement equal to minimum area of reinforcement. And also I am not doing the same step for mu positive, because here mu positive will be 60, so the AST will be also less than 600, and we will have to provide 600 mm square there also. So in both the cases of negative and positive, we take reinforcement equal to minimum reinforcement. We assume the diameter and calculate the spacing. Therefore provide 10 mm dia bars at 130 mm center to center in the bottom portion, and in the bottom face near the midspan, and in the top face near counterfort also. I have written both the reinforcement in one line only. So I will draw the diagram here. If this is your heel slab, this is your counterfort here, and this is also counterfort here, and this is the stem here. So the reinforcement are designed in such a way that in the bottom face tension will occur in the midspan. So reinforcement is provided here in the midspan, which I have shown here in this plan, and in the top face we provide reinforcement like due to negative moment near the supports. So I have shown these reinforcements in two phases, like in bottom face and in top face. In bottom face we have reinforcement in the midspan, and in the top face we have reinforcement near the supports. And also to support these horizontal reinforcement, we need to provide some reinforcement in the perpendicular direction also, like this, to form a mesh so that it is easy to hold this reinforcement. So we provide distribution reinforcement in the perpendicular direction. I have not designed it, just taken it to be any value which is equal to AST minimum. So now the design of toe slab is done in the same way as in cantilever retaining wall. So we calculate this is the P maximum. We calculate the pressure at the fixed end using linear interpolation. We find the moment here at MAB using equation sigma MAB is equal to 0, equation of equilibrium, and due to this moment we do the check for the thickness required, and we provide the reinforcement due to this value, which is coming out to be 440 mm square, which is less than the required minimum 600. So here also we provide 10 mm dia bars at 130 at the bottom face. So always whenever you are designing the reinforcement, keep noting in your mind where we are providing this reinforcement. For example, If we start with the stem, the main reinforcement was provided near the midspan on the outer face and near the supports on the inner face, and the other reinforcement was the distribution reinforcement. In the heel slab, the main reinforcement was provided in the bottom bottom face near the midspan, and in the top face the reinforcement was provided near the counterforts, and distribution reinforcement was provided in the perpendicular direction. In toe slab, the main reinforcement is this reinforcement provided on the bottom face. Okay, now you need to keep that in mind. Now we design the counterforts. So counterforts are designed as triangular beams of varying depth supported on the stem and heel slab. So first of all we find the D. So for that we need to use trigonometry. This value is the height of stem, 5 meter, and this is the base width of your heel slab, 1.8 meter. So first of all we get this angle theta. Theta is tan inverse of 5 by 1.8, so we get the value is to be 43.71. And for finding D, look at the smaller triangle B'(C). D will be 1.8, that is hypotenuse into sine theta. Sine theta will be perpendicular upon hypotenuse, that is D upon 1.8. From that we get D. So D is 1.243 meter. Now maximum moments on cantilever on the counterfort will be half into Ka gamma h, that is this is the cantilever moment acting at the base of your stem, into L, which is the spacing of the counterforts. We get this value as 312 and we multiply it with 1.5 to get the design bending moment. We calculate the reinforcement due to this. Now this reinforcement is coming out to be 1114 mm square. Now note here carefully, here B will be 300 because the width of this counterfort is acting now like a beam. So this width of beam is 300 mm and the depth of this beam is 1243 mm. We have calculated here. So keep this in mind. This B is not 1000 as we take in the previous cases. Now this is a slab, not a beam. So what is the after this step we need to find the minimum AST and check that with this. So in case of beams, the minimum reinforcement is calculated by this formula. I hope you remember it, 0.085 BD upon Fy, which is coming out to be 763 mm square. Therefore I am repeating, don't take this AST minimum to be 0.12% because this counterfort is not a slab, it is a triangular beam. So AST minimum is 763 and our AST required is 1114, so we take AST is equal to 1114, sorry, it will be 1114 mm square. Now as it is a beam, in case of beam we do not calculate the spacing but we calculate the number of bars. So assuming diameter of bar as 20 mm, we calculate the number of bars. Number of bars is total AST required upon area of one bar, which is coming out to be 3.5, and we rounded off to 4 bars. Therefore in this counterfort the main reinforcement is provided in the form of these inclined bars. In the photograph also I had shown you some in the counterfort there were some inclined bars provided. So these are the inclined bars. We can curtail few bars at top as moment in beam will reduce. So as we know, this is a cantilever bending moment. It will keep reducing as we move towards the top of your counterfort. Therefore the bars in the beam can be curtailed after a particular point. So we don't need to calculate the height of this particular bar for now. We just write that we curtail out of the 4 bars, we curtail 2 bars like this, or we can curtail alternate bar also, it's up to you. So this is the main reinforcement in your counterfort. Now we have to design horizontal ties and vertical ties so that the pressure, lateral earth, active earth pressure does not separate the stem from the counterfort, and the downward weight of soil does not separate the heel slab from the counterfort. So first of all we will design the horizontal ties. The horizontal ties due to the lateral earth pressure try to separate counterfort from the stem. So what is lateral earth pressure? It is 25 kilonewton per meter square, and total earth pressure taken by the counterfort will be 25 into 3 minus 0.3. 3 minus 0.3 is basically the center to center spacing between the two counterforts. So we get the factor tensile force T. Now we design the ties not due to the moment but due to this force T. So reinforcement to resist this horizontal tension is calculated as T is equal to 0.87 F by AST. I hope you remember this formula. This is the formula for calculating tensile force in any particular RCC element. D is equal to FC upon AST, where FC is Fs into AST, where Fs is 0.87 F5. So we know T, then we calculate ASTH 281, and as these are ties are always calculated in the form of spacing. We assume the diameter of bar and calculate the spacing. So spacing is coming out to be 279 and we take it as 260. So horizontal ties are provided like this with the spacing of 260 mm center to center. Similarly, we calculate the vertical ties. For this we will first found the downward pressure. Downward pressure is acting as 87.5 minus 16.94. We have calculated it already in the design of heel slab. We calculate the factor tensile force and we calculate ASTV, which is T upon 0.87 Fy, and we calculate the ASTV. So we are getting 10 mm dia bars at 260 mm center to center. So therefore this type of mesh is provided in the counterfort. So this is the summary of all the reinforcement which we have provided. I will start with the stem. So in the stem, the main reinforcement are these dots. So if you keep on comparing it with that of a cantilever retaining wall, in a cantilever stem the main reinforcement was this, and these were the distribution bars, horizontal bars. Now it is exactly opposite for this counterfort stem. In counterfort stem, these horizontal bars are the main reinforcement provided on the inner face, provided on the inner face near the supports, and on the outer face near the midspan. Okay, so as this is a cross section, we cannot distinguish here what is the midspan and what is the support area, but for that you can draw here, which I have already drawn in the previous diagram, the L section of your stem showing the reinforcement. This is the inner face reinforcement, and on both the supports, and this is the midspan reinforcement in the outer face. So I hope this is clear to you. So as you can see, we have two main reinforcements. This blue dots showing 10 phi at 200 mm center to center, main reinforcement on outer stem, and it is increased, the spacing increased to 300 mm center to center. Similarly, 10 diameter at 200 center to center is the main reinforcement provided on the inner side, and the vertical bar, this and this, are the distribution steel provided and taken as the minimum reinforcement, which is coming out to be same, that is 10 diameter at 200 center to center, which is provided in the vertical direction. So these are extended up to the slab. Now we'll look up at the heel slab. In the heel slab, the main reinforcements are the horizontal reinforcement provided on the bottom face near the midspan and on the top face near the supports or near the counterforts. So for heel slab also you need to make a diagram like I did previously with the heel slab, showing the plan of your heel slab of top face and bottom face separately. Now this horizontal bar is this type of, not horizontal, but this bar is the distribution bar. This is also the distribution bar. So this is the reinforcement of your heel slab. Now we look at the toe slab. In toe slab, note here very carefully that in toe slab this is the main reinforcement, and in the heel slab these dots are the main reinforcement. This is a very important point to note here. In the heel slab this is the reinforcement, main reinforcement, like this, and in toe slab this provided along the length of your toe slab in this direction is the main reinforcement. So I hope you understand the difference, and these dots show the distribution reinforcement. In the top face also we do not require reinforcement, but we provide minimum distribution reinforcement here also. So this is all about the section of your retaining wall with all the components. Now we look at the detailing of counterfort. These blue line 1 and this are showing the inclined bars provided along the face AC of your counterfort, which is the inclined face, which are 4 20 mm main reinforcement and 2 it should be opposite. This it should be 4 and it should be 2, because we have curtailed 2 bars here, so it will be 2, not 4. So kindly correct this. And all this mesh is the 10 diameter at 260 center to center. These are the horizontal ties, and 10 diameter at 260 center to center are the vertical ties. And this reinforcement is taken inside the stem. As you can see, this dotted line is showing the face of the stem. Some of this reinforcement is taken inside the stem so that the stem is well connected with the counterfort, and similarly the heel slab is well connected with the counterfort. Here also some reinforcement has been extended to the heel slab. So, and this inclined reinforcement has also been taken into the stem. So I hope all this detailing is clear to you. This was the design of counterfort retaining wall.